So you get on a Ferris wheel. The wheel has a diameter of 10 meters, and the seats are 1 meter above the ground. That's always good. It's not good to have the seats run into the ground. And it takes 60 seconds for the wheel to go all the way around. Sketch a graph of the height of the wheel above the ground in relation to time. So the first thing you have to determine is one of these is going to be time and one of them is going to be height. Which one's dependent, which one's independent? The height is dependent on the time. So we'll put under here, the independent one is your time, and over here we'll label this as height. We'll start at time 0. Where are you at time 0? How high above the ground would you be at time 0? 1 meter. Because it makes sense that you wouldn't like hop on the top, right? You would get on the bottom. So at 1 meter, sometimes we go height in meters and time. We'll put an S there for seconds. Perfect. So at 1 meter is where you get on. Can you tell me another time and another height that you know? For example, could you tell me, where are you at 60 seconds? Where are you at 30 seconds? Where are you at 80 seconds?
Well, 60 seconds, you're back at 1 meter.
So if I put 60 right here, I pick a random spot, I would be back at 1 meter at 60 seconds. How high would you be? Where would you be at 30 seconds? At 10? Close. The diameter is 10. So does it make sense that at 30 seconds you'd be right at the top?
Yes.
Okay. So how high above the ground is that? Not 10. 11, right? Because you started 1 meter. The diameter was 10. That would make it go up to 11 meters. Where would you be at 15 seconds? And sometimes it's nice to draw a picture of it. Here's the Ferris wheel. We're starting 1 meter above. At the very top, this would be at 11 meters. Here you are, all happy, on the Ferris wheel. We're saying that if it takes 60 seconds to go all the way around, 30 seconds you would be at the top. Shouldn't do that. Where would you be at 15 seconds? Right there. Where's that middle?
5.
Close. This whole,
Oh, 6.
yeah, this whole thing is 10, right? So half of it would be 5. If you started at 1 meter above the ground and went up 5, this in the middle would be at 6. Would you agree you'd be back at 6 at 45? Where would you be at 120?
1.
Well, you'd be at 1. Where would you be at 90?
11.
Does it make sense that this sort of repeats itself over and over again? And we keep on going like that.
Yeah.
So the graph isn't a circle, even though a Ferris wheel travels around in a circle. The graph that we draw, with time happening this way, goes up and down and up and down. And this is a function because every x value, when you go up, you hit only one y value. It would be bad if this wasn't a function. That would mean like at 30, you would be here and here at the same time. Something bad would have had to happen on the Ferris wheel for half of you to be at 30 and half of you to be, yeah, that would not be good. And we would definitely say this Ferris wheel is not functioning correctly. At that point on. Okay. So one of the things that we have to figure out with these graphs is what's going along your x-axis, what's going along your y-axis, what's dependent and what's independent for drawing this. So Sasha goes for a ride on her bicycle. She accelerates until she reaches a speed of 20 kilometers an hour. Then she rides at this speed for 30 minutes. Sasha arrives at the bottom of a hill, and her speed decreases to approximately 5 kilometers per hour for 10 minutes. She stopped at the top of the hill for 10 minutes. Sketch the graph of her speed as a function of time. Okay, there's a lot of information here. So first of all, we need to decide what we're going to put on the y, what we're going to put on the x. The x one is our independent, the y one is dependent. So in this case, what depends on what?
Speed
Kilometers depends on the time.
Right, the speed here, they tell us, and the time. Okay, this time is in, what do they give us? In minutes, right? Time is given in minutes, and the speed is given in kilometers per hour.
And there's something wrong with time.
Oh. Yeah, that is not very nice. Yeah, there's something wrong with yours. You can try to sketch it on this page.
How long does it take for her to accelerate?
Okay. Well, now let's read through each of the things. She starts at what speed? 0. So times 0, her speed is 0. So we can put a 0 here and a 0 there and say that's our starting point. She accelerates, which means she's going to get faster until she reaches a speed of 20 kilometers per hour.
So how long?
And does it tell us how long that takes? No. So we have to make some sort of, right? Sometimes these questions have data missing, so we're going to have to make some sort of estimation. Total time, she rides at this speed for 30 minutes. Then we've got bottom of hill, 10 minutes. Stop at the top of the hill for 10 minutes. So it looks like we need to have probably about an hour on here. So what would you think would be a reasonable amount of time to accelerate to get to that speed? 2 minutes? Okay.
2.5 minutes.
So just looking on here,
We go up by 5.
10, 15, if we go up by 5s, 5, 10, 15, 20, 25, 30, yep, if we go up by 5s, things seem to be good. Why don't we give her 5 minutes to accelerate to 20? How fast does she go in total? 20 is the fastest she gets. So I'm going to go 5, 10, 15, 20. So you're saying she accelerates until she gets to 20 in 5 minutes. Then what does she do?
Stays there for 30 minutes.
Stays there for 30 minutes, so that would go 10, 20, 25, 30, up to 35 minutes. Would you agree? Not 30 minutes, because we are only staying there. So it's now she's going at that speed for 35 minutes, up to 35 minutes, 30 minutes longer. She arrives at the bottom of a hill, and her speed decreases to approximately 5 kilometers per hour for 10. Wow, this is badly, I'm sorry. The English in this question is terrible. Because she's going to the bottom of the hill, but her speed decreases.
Yeah, that doesn't make sense. You would think it would increase.
So I'm trying to imagine this. She is starting here, she's going down a hill, reaches the bottom, and then goes back up a hill, and stops at the top of it. So this is the hill. This might make sense.
Yeah, but why would she do this?
She arrives at the bottom of the hill and her speed decreases to approximately 5
Oh.
kilometers an hour. Because she's at the,
Oh,
she
as she's
arrives at
up
the
the
bottom, and that means she's going back up. So as she is, we're going to say that with the hills here, this is the point where she's down here. Okay? She reaches that point, now she's starting to go up the hill, and because she's going up the hill,
Can you give her 5 minutes?
well, let's say she's going up the hill for 10 minutes, and over those 10 minutes, so from 35 to 45 will represent this part, her speed starts slowing down to 5. So I'm going to have her slow down to 5 minutes, to 5 kilometers per hour.
Over 10 minutes.
Because it took 10 minutes. So she's got lots of momentum, but as she's going up the hill, her momentum is slowing down and her speed is slowing down. Then she stops at the top of the hill for 10 minutes. So she slows down to here
And then she stops.
and she stops, so her
She's on the
speed
bottom
needs to
of the-
go
Straight down.
straight. Well, we can't ever go straight down. Because going straight down in a function means like hitting a wall, right? You don't want your speed to instantaneously change from something to something. So I'm going to give her 5 minutes to go to the bottom, and then she stopped for 10 minutes. Now this had some interpretation here in this question. When I give you these ones on a test or a quiz, I will be clearer than this example. Okay? But this could be an idea of what's happening. Now, given the picture of the hills, does this make sense that you would increase in speed? Probably, if I was drawing the hills here, if I started on a hill that's going down, I would increase in speed. And then to maintain the same speed, it's probably flattening out for a while. Because your speed is continuing, you can keep that speed. And then going up a hill.
I don't know, I feel like once you're at the bottom, then your speed would, like, at the bottom of the hill, your speed would start to slowly increase a little bit.
Maybe, or maybe it's a slightly down so you can just like coast and keep your speed. Mhm. The graph below shows the height of water in a bathtub as a function of time. What is happening from A to B?
The bathtub is getting filled up.
Bathtub's getting filled up. So I'm going to AB. The tub is being filled. What about B to C?
They're turning off the water.
Well, the height is still going, like,
But as they're turning it off, it's like,
oh, maybe slowly turning off the water?
well, we don't know what the time, like, units are.
Okay. That could work. I also imagine from B to C, the person is like, one leg goes into the tub. And it's too hot. So you just sort of freeze for a little bit at that moment. Because do you test the water before you get into the tub? No, you just jump right in?
Touch it with your hand.
Test it with your hand. Maybe they're testing the water.
Maybe that's a hand.
And so with these questions, you have a little bit of freedom to describe things. It needs to go up a little bit, right? You're about to get in and you knock over the shampoo container. That could make the water go up a little bit. So we have some freedom here, okay? And if you want to get super creative, I don't know what else. You accidentally drop your towel in the water. That's a good idea. You decide not to take it out. Okay? Then from C to D,
You decide to not take it.
from
Maybe
C
you're
to
adding
D,
like a bath bomb or something.
I think from, yeah, B to C could be the bath bomb, something little. Okay? C to D, I think there's a logical one here.
You're getting
Person gets into the water. Is it? Okay. Person gets into the tub. That would make the height go up. C to E, you say they're chilling?
bathing.
They are chilling.
Yeah.
Fine. What units probably here? What do you think units would probably be on time? Minutes probably would be logical. Days would probably not be too logical here. Yeah, it took 3 days to fill up your tub. And then you spent 10 days in the tub. Okay. E to F.
No, it's E to H.
Oh, does it say E to H? Oh yeah, because they're basically
Getting out and draining.
E to H. Getting out. And draining the tub. Makes sense. Yes. All this water is too much. I understand. Okay, now's your turn to be creative. This is for people that love English. This is your chance to write a story.
No. Right. This is upsetting.
For those of you that like math, this is your chance to just apply mathematics to a graph and write a boring story. Okay? There's distance in kilometers and time. You get to do whatever story you like.
Why? Because it's seconds? Why?
Yes.
Well, the kilometers, it can't be,
No, totally.
running.
So the two stories that you have to write are totally different. One has distance.
Okay, so what order is it?
You're gonna go Jimmy?
I'm going with Gilbert.
Gilbert?
Gilbert what? Gilbert ran to the, like, how did it start? So from this first bar up, how did it start? Gilbert ran. Wait. You need to tell the second, right? Kilometers in seconds. I I think you should drive. Not run. Yeah, 'cause there's some Gilbert,
Thomas. How many we got right out of the 12?
Stop for a little bit. So that's what the stop would be.
I don't get how to figure this out.
We need to say
No.
how long it took.
So the same thing we've been doing here.
Yeah.
You read one,
I guess.
and you try to figure out which one matches the best. You have to draw that graph. They're hard. They're not easy. Hmm? It'll make you think, and then some of them you can't match for a while. You gotta like, some are easier than others.
Yeah. You have to read them all over the place.
Multiple times.